The important thing is not to stop questioning. Curiosity has its own reason for existence. That's Albert Einstein, of course. And it feels like the perfect way to kick off today's deep dive. Because haven't you ever looked up at the stars and just, well, wondered about those huge questions like where is the middle of it all? Or how fast is the universe expanding? And maybe the biggest one, what's beyond everything? Today, we're jumping into one of the really big pressing problems in cosmology right now, what scientists call the Hubble tension. And look, this isn't just some, academic thing. It's like finding a crack in the foundations of how we think the universe works. It hints maybe we're missing something pretty fundamental. So if you're studying for the UPSC, trying to keep up with science and tech for mains or prelims, or honestly, if you're just curious about the cosmos, this is definitely something you'll want to understand.
Right. And the Hubble tension, it really boils down to this disagreement about, well, a single number, how fast the universe is expanding right now. So we're going to dig into the history, how we even found out it was expanding, then look at the pretty ingenious methods they use to measure things out there. Yeah. And crucially, why this difference in measurements is causing such a headache for cosmologists. A bit of a cosmic detective story, really.
Okay, let's start at square one then. How did we even figure out the universe was expanding? I mean, it seems obvious now, but it surely wasn't always the case.
No, absolutely not. It was a huge shift. You have to go back about a century. You had George Lemaitre in 1927, and then Edwin Hubble in 1929 doing observational work. And they found something really startling. Pretty much all galaxies are moving away from us. And here's the kicker. The faster they're moving, the further away they seem to be. It's a direct relationship.
Mm-hmm. So further equals faster. And that's the Hubble-Lemaître law, right? Defined by this Hubble constant, h0. It's measured in kilometers per second per megaparsec. Can you break that unit down for us? What does that actually mean?
Yeah, sure. It sounds a bit intimidating, but think of it like this. A megaparsec is just a really, really big distance unit, about 3.26 million light years. So h0, the Hubble constant, tells you how many kilometers per second faster a galaxy is receding for every extra megaparsec of distance it has from us. It's basically a snapshot of the expansion rate today. But what's really fascinating, as you hinted, is that theory actually got there first. This experimental finding was predicted years before Hubble published his data.
Ah, right. Theory leading observation. Always neat when that happens. So who predicted it? What was the theoretical basis?
Well, back in 1922, you had Alexander Friedmann, a Russian physicist. He was looking at Einstein's equations for gravity, and he found solutions that, well, they weren't static. They implied the universe had to be either expanding or contracting. Then Lemaitre, in 1931, he kind of ran the film backwards. He reasoned if things are expanding now, they must have been incredibly dense, packed together in the past. And building on that, Georgy Gamow argued that this initial state wasn't just dense, it had to be incredibly hot. And that's sort of the genesis of this dynamic, evolving model of the universe.
Wow. I mean, those ideas must have seemed pretty radical back then. Did everyone just jump on board?
Oh, definitely not.
Right.
No, there was a lot of skepticism. You had prominent astrophysicists like Fred Hoyle, who favored a different idea entirely, this steady state theory where matter was sort of continuously created as the universe expanded. And funnily enough, it was Hoyle in a BBC radio show in 1949 who actually coined the term Big Bang. He meant it dismissively, almost mockingly, for Lemaitre's and Gamow's theory.
Huh. That's ironic. And now Big Bang is just, the term we use for that whole theory of expansion from a hot, dense state. Shows how language evolves, I guess. Okay, so if the Big Bang is accepted and it explains expansion, where does this Hubble tension, this pain of 21st century cosmologists, actually come from? What's the specific problem?
Right. The problem is getting the exact number for that expansion rate, for h0. The devil's really in the details here. I mean, look at Hubble's first estimate. He calculated something around 500 kilometers per second per megaparsec.
500, compared to today's values, which are more like 70-something.
Exactly. Around 73 kilometers MPC from many modern methods. That massive difference in the early days just underscores how incredibly hard these cosmic measurements really are.
Yeah, 500 versus 73 is. Wow. So how do they measure these things accurately today? Getting those distances must be the real challenge, right?
That's precisely it. Measuring the speed, the velocity is relatively easier. Use redshift. The light stretches as objects move away, like the Doppler effect for sound.
Yeah.
But distance across billions of light years, that's tough. There's no cosmic tape measure. So astronomers rely on these things called standard candles.
Standard candles.
Right.
Things where you know the actual brightness, the luminosity.
Exactly. If you know how bright something truly is, you can figure out how far away it is just by seeing how dim it appears to us. It's like knowing the wattage is a light bulb.
Yeah.
And the workhorses here are mainly type Ia supernovae. These are exploding white dwarf stars. They're incredibly bright and pretty consistent. And Cepheid variable stars.
Cepheids. Those are the pulsating ones.
That's right. They're supergiant stars that pulsate. And crucially, the time it takes them to pulse is directly linked to their actual brightness. Very useful cosmic yardsticks.
Okay, so Hubble used Cepheids too, but his number was way off. What were the mistakes back then?
Well, he was a pioneer, but working with limited tech and knowledge.
Yeah.
First, they didn't know back then that there are actually different types of Cepheids with slightly different brightness relationships. That messes things up. Second, he didn't fully account for all the dust between stars and galaxies. Dust absorbs light, making things look dimmer, and therefore seem farther away than they are. And sometimes, what he thought was a single Cepheid star was actually a whole cluster of stars, which obviously skewed the brightness measurement.
Ah, okay. Lots of potential pitfalls.
Definitely. So modern measurements using Hubble Space Telescope, other observatories, refining techniques, understanding the dust, they consistently landed on values for HCO, mostly clustering between, say, 70 and 74 kilometers MPC using these standard candle methods.
But then things got even weirder, right? Because it turned out the expansion wasn't like steady or slowing down. It was speeding up. That seems totally backwards.
It really does. It was a Nobel Prize-winning discovery in 1998 by Perlmutter, Schmidt, and Rees. They were looking at those type Ia supernovae, the really distant ones, and they found they were dimmer than expected, even accounting for the standard expansion models. The only way that made sense was if the expansion of the universe itself has been accelerating over the last few billion years.
So something is actively pushing things apart, overriding gravity on the largest scales.
Pretty much. That's what we now label dark energy. Some kind of mysterious pressure permeating space. We don't know what it is, but it seems to be responsible for this acceleration. And this discovery also means the Hubble constant isn't strictly constant over all of cosmic time. It changes. So technically, we should probably call it the Hubble parameter, but H0 refers to its value today.
Okay, wow. Dark energy, accelerating expansion. But there's another whole way to probe the universe's history, isn't there? Something completely different from looking at galaxies moving away now, like an echo from the very beginning.
You're talking about the cosmic microwave background, the CMB.
Yeah.
It's incredible. Back in 1965, Arno Penzias and Robert Wilson were working with a new microwave antenna, and they kept picking up this faint, persistent background hiss, noise coming from everywhere in the sky, day and night. They checked everything equipment, even famously pigeon droppings in the antenna horn.
Pigeon droppings?
Yeah. But the noise wouldn't go away. They eventually realized it was cosmic in origin. An accidental discovery, but absolutely profound, got them the Nobel Prize in '78.
And this noise, the CMB, it had actually been predicted, right?
It had, by Gamow and his colleagues, back in the late 1940s. It follows directly from that hot Big Bang idea. See, in the very early universe, it was so hot and dense, it was like an opaque fog, a plasma. Light couldn't travel freely. But as the universe expanded and cooled, about 380,000 years after the Big Bang, it cooled enough for atoms to form. Suddenly, space became transparent. And the light that was present then, the thermal radiation from that era, was finally set free to travel across the cosmos. At that moment, the universe was about 3,000 Kelvin. Gamow predicted that due to cosmic expansion stretching the wavelengths of that light over billions of years, today it should look like radiation from a body that's only about 3 Kelvin, just a few degrees above absolute zero.
And he was right.
Astonishingly close. Modern satellites, COBE-E, WMAP, Planck, have measured it with incredible precision. The average temperature is 2.725 Kelvin. It's this almost perfectly uniform glow across the entire sky.
Almost perfect. So there are slight variations.
Tiny ones. That's the other crucial part. There are minuscule temperature fluctuations, differences of just a few hundred microkelvins from one spot in the sky to another. These aren't errors, they're real. They're the imprints of tiny density variations in the very early universe. Basically, the seeds that eventually grew through gravity into all the stars, galaxies, and galaxy clusters we see today. Finding and mapping these tiny fluctuations, that was another Nobel Prize for George Smoot and John Mather with the COBE satellite.
Okay, so this CMB, this ancient light, it's not just a temperature reading. It's like a map of the baby universe containing information about its initial conditions.
Exactly. And here's where it connects directly back to our Hubble tension problem. Because we have this incredibly detailed map of the early universe from the CMB, And we have our standard model of cosmology. It's called lambda CDM, representing dark energy, lambda, and cold dark matter. Using this model, which describes how the universe evolves based on its ingredients like dark matter, dark energy, regular matter, and radiation, scientists can take those initial conditions seen in the CMB and essentially run the clock forward. They can calculate, based on that model and the early universe data, what the expansion rate should be today, what age 0 should be.
Okay, so the CMB gives us a prediction for age 0 based on the early universe and our best model.
Precisely. And the most accurate measurements of the CMB, primarily from the European Space Agency's Planck satellite, give a very precise prediction. Planck data calculates age 0 should be 67.4, plus or minus about 0.5 kilometers per second per megaparsec.
67.4, okay. But wait, you said the standard candle measurements, the Cepheids and supernovae, were giving values between 70 and 74, mostly around 73.
That is the Hubble tension, right there. You have one set of methods looking at the local universe relatively nearby, using standard candles, giving you about 73, and you have another method looking at the early universe via the CMB and using our standard cosmological model to extrapolate forward, giving you about 67.4.
And those numbers, they just don't overlap, do they? The error bars don't meet.
They don't. It's what physicists call a statistically significant tension. It's more than just a measurement quibble, a difference of around 10% in a fundamental parameter like this. It's a big deal. It strongly suggests that either our measurements are wrong in some subtle way we haven't found, or our understanding of the physics connecting the early universe to the present day, our standard cosmological model might be incomplete. Maybe we're missing something about dark energy or dark matter or some other physics in the early universe.
Okay, so this is a genuine puzzle, a crisis even. What are scientists actually doing to try and solve it? What's the latest?
Well, they're tackling it from multiple angles. A lot of effort has gone into just double-checking and refining the measurements themselves. For example, back in 2019, there was a big push using the Hubble Space Telescope to recalibrate those standard candle distances even more carefully. And guess what? They landed right back at 74 kilometers MPC, strengthening the tension.
Right. And then came the James Webb Space Telescope, JWST. Everyone hoped its super sharp vision would finally sort this out. What did JWST find?
Yeah, hopes were high. In 2024, results came out from JWST looking at Cepheids and supernovae with unprecedented accuracy. And surprise, the JWST results basically confirmed the earlier Hubble results. They were totally consistent with that 70-74 range. So JWST didn't resolve the tension. If anything, it made the standard candle side seem even more robust.
Huh. So JWST agreed with the local measurement.
Mostly, yes. Although interestingly, a very recent study just out about a month ago also used JWST, but analyzed some different types of standard candles. And that study estimated 8.0 as 69.03 plus or minus 1.75.
69. Okay, that's kind of in the middle, isn't it? Does that help?
It maybe weakens the tension slightly because its error bars might just touch the Planck value's error bars, but it certainly doesn't eliminate the tension altogether. It's still not a comfortable agreement.
So if our best telescopes seem to be confirming both sides of the measurement conflict, or at least not clearly resolving it, what else could be going on? Are people looking at changing the underlying theory, the cosmological model itself?
Absolutely. That's where a lot of theoretical work is happening now. People are exploring all sorts of possibilities. Maybe, for instance, our location in the universe is a bit unusual. Perhaps we're near the edge of a large, underdense region, a cosmic void, which could affect local measurements.
Like living in a less crowded neighborhood makes the traffic look faster elsewhere.
Kind of, yeah. That's one idea. Another popular avenue is modifying dark energy. Maybe dark energy wasn't constant throughout cosmic history. Maybe its properties changed, particularly in the early universe. There were some intriguing, though still debated, findings earlier this year suggesting dark energy's influence might indeed be changing over time, which could potentially ease the tension if confirmed.
Okay, that sounds plausible. Anything more out there?
Oh, sure. There are always more extravagant ideas, as cosmologists sometimes call them. Things like modifying gravity itself on cosmic scales, or proposing new types of particles or fields in the early universe. Even ideas like the entire universe having some sort of global rotation.
Whoa, global rotation! Okay, that's pretty wild. But none of these have emerged as the clear solution yet.
Not yet. Each proposed solution seems to solve the Hubble tension, but might create other problems or lack definitive supporting evidence. It's still very much an open field. The Hubble tension remains probably the most significant crack in our standard picture of the cosmos right now.
So, wrapping this up, what's the bigger picture here? Are we looking at maybe needing a whole new revolution in cosmology, like Einstein relativity was to Newton's gravity? Or is this more like finding a subtle flaw that needs tweaking?
That's the billion-dollar question, isn't it? You look back at the 20th century, discovering relativity, figuring out the universe was expanding, discovering dark matter, dark energy. Those were fundamental worldview-altering shifts. The 21st century so far has been more about precision cosmology testing and refining that established framework.
But now these cracks, like the Hubble tension, are really showing. And you also mentioned the JWST finding those surprisingly mature-looking galaxies in the really early universe. So that's another headache for the standard model, right?
Exactly. That's another major tension point. So you have the Hubble tension about the expansion rate now and these impossible early galaxies challenging our models of structure formation then. It really does make you wonder, are these signs that our standard lambda CDM model, while incredibly successful, is reaching its limits? Does it need a major overhaul, a paradigm shift? Or are we just missing some crucial details about the initial conditions, or the nature of dark energy, or maybe some unknown physics from that very first second after the Big Bang? Could tweaking those solve it? It's what keeps cosmologists up at night.
It's a fascinating time to be following cosmology, that's for sure. And the universe, well, it clearly still holds plenty of secrets. Understanding this Hubble tension, this ongoing puzzle, is really key to grasping where cutting-edge science is heading. And for anyone preparing for UPSC, grappling with these kinds of current scientific debates and their technological implications is obviously vital for mains, maybe even prelims too. Plus, it just helps you appreciate the incredible and still mysterious cosmos we live in. We really hope this deep dive has given you a clearer picture of this cosmic conundrum and maybe sparked even more questions. If you found this exploration useful, please do give this deep dive a like and definitely subscribe to the deep dive for more explorations like this one. Let us know in the comments if you have questions or if there are other complex topics you'd like us to tackle next.